Okay, so let's start the sessions of the last day. And okay, so let me introduce Professor Coccia. Professor Eugenio Coccia is the founder of the School of Advanced Study Gran Sasso Science Institute, and its rector since 2016. He's a physicist with expertise on astroparticle physics with a focus on gravitational wave experiments. He is recognized for the development of cryogenic detectors of gravitational waves and is one of the authors of the recent discovery of gravitational waves and of the first observation of black holes. He has been full professor at the University di Roma Tor Vergata from 2000 and chair of the INFN Scientific Committee on Astroparticle Physics and director of the INFN Gran Sasso Laboratory and president of the Italian Society of General Relativity and Gravitational Physics and chair of the Gravitational Wave International Committee, and among others responsibilities. He has been given lectures and seminars in universities and research centers all over the world, and is the author of about 300 scientific articles in international journals and editor of 6 books in the field of astroparticle physics. He is a member of the Academia Europaea Honoris Causa and a fellow of the European Physical Society. So let's welcome Professor Coccia. So the title of the talk is The Birth of the Gravitational Wave Astronomy.
Good morning, thank you for the invitation. I will tell you about the birth of the gravitational wave astronomy. Is a very exciting moment for people working in this field, and I will try to transmit some emotions also of why this is such a magic moment. Well, what happened at more than 1 billion light years from Earth was something like that. This is slower than the real action. However, 2 black holes, they have inspired the one toward the others, and at the end of this sort of cosmic dance, they have merged in a single big black hole. No photons came out from this event. So how we know this event happened? We know because of the existence of waves in space propagating the speed of light, which are waves made of space-time perturbation. And this is what we detected in September 14, 2015. But let us go a little bit earlier in time. This is the notebook of Galileo Galilei, and I like to show you this because, in my opinion, this is the beginning of modern astronomy. I mean, astronomy not made with the naked eye, but with an instrument, a telescope. The first time that a telescope was directed towards the sky, and what you have seen changed our concept of the universe, because no one before observed what he observed in January 7, 1610. This is in Italian, of course, so it's a pleasure for me to read it, but I will translate for you. He says, 7 of January 1610, Jupiter, Giove in Italian, Jupiter was, si vedeva col cannone. The cannone was the name that he gave at the beginning to the telescope. And 3 fixed stars. So it was possible to see Jupiter with the telescope, but also 3 new stars. You see 1, 2, and 3. And this is Jupiter, you see eye of Jupiter. And he says of these stars, no one was possible to see without the canon. So it was a discovery. What is this? I mean, this is something not predicted. Was not reported in any Babylonian, Assyrian, Greek, Egyptian, in the Bible. Was the discovery of the ignorance, if you want. So there is something in the universe we don't know really. And this is why this was only the beginning of a long path up to today. He say more. He say the day 8th of January, so the day after, it appeared like that. So this was Jupiter, and the 3 stars were displaced. All 3 on the right. This was even more incredible. So he realized that these 3 stars were around Jupiter. So Jupiter was a solar system in its own. It was incredible at the time, because even if in a Copernican view, the Sun has this privilege to have all the other celestial objects around him. But this is what Jupiter seems to have also. And this was the first sign of the universality of gravitation, which holds everywhere. And he adds that this motion of the 3 stars was opposite to the motion of the entire sphere of the stars. Then he adds that the day after 9 was cloudy, dot. The day 10, but he wrote, however, he said that the day 10, the day 10, you see, the position changed and one of the stars was in front of Jupiter. This was an incredible first time in the history of astronomy. I mean, it is the beginning of what we call the electromagnetic astronomy, the astronomy with the photons. Then, what must be added, I think, is how we see gravity, how we see gravitation, and why gravitational waves are a new parameter, a new entity in this history. So this was the original drawing of Isaac Newton, and is another revolutionary drawing, because he says, Newton, at a time in which the terrestrial nature and the celestial nature were completely different, he made a fantastic synthesis, saying that the same laws holds everywhere, on the earth and in the sky. And this is what this drawing says, because if you go on the top of the mountain and you throw a stone, of course the stone falls on the earth. If you throw it with more force, let's say, with a higher speed, then falls a little farther, and then a little farther. There is a certain limit of speed in which if you give it, the stone continue to fall, will fall forever without impacting on the Earth, because the Earth dimension is finite. So these things means that the same force which holds on the Earth, for which a stone falls on the Earth, is the same for which the moon goes around the Earth. The moon is falling on the Earth, and the Earth is falling on the Sun. This is why this is a fantastic breakthrough in the history of science, in the history of philosophy, in the history of mankind. So with this law, Newton described all the solar system. And through this law, we are able to predict the position of every satellite, every planet in 1,000 years from now. It works very well. It works so well that you can say what else one should say about gravity. We know everything. Well, we don't know everything, and this man is what he introduced a new concept for which the gravity force does not exist. This seems an impacting statement, but actually what he says is that two people which goes in a parallel line, thinking to be in flat space-time, and experiencing, looking the fact that they are not going to parallel line, actually. They are near and near, so they can think this is because of a force of attraction, while the view of Einstein is that maybe there is not a force of attraction, maybe there is a geometry which is different respect to the one we think. In fact, while in a flat space-time, you must, in a two-dimensional flat space-time, you must interpret this as a force attracting two people. If you change the geometry and you think on a spherical geometry, then the attraction, it is natural because of the geometry. There is no need to introducing a force. This is the view of Einstein, which is expressed by a complicated equation, which means simply that the geometry of space-time, the distance between space-time events, depends on the presence of masses and energy. So if this is zero, this is a flat space-time where we know where ray of light go parallel. But if in this universe, in this place, in this regional space, there are masses, then the geometry is no more the flat one. And actually, if there is a mass, like the sun, for instance, what happens, following Einstein, is this is a two-dimensional representation just to visualize. Of course, the real curvature, the real deformation, is in three space dimension plus time. In the word of a famous physicist, John Archibald Wheeler, space-time tells matter how to move, and matter tells space-time how to curve. So if it is the sun, then the Earth goes around the sun, not because of a force of attraction, but just because the geometry of the space-time around the sun, it constrains the Earth to move in this way. Well, this is necessary, and necessary to introduce this basic concept of general relativity. There is no force in a flat space-time, simply there is a curved space-time, no force. Curved space-time explains everything. So in this curved space-time, a mass which is very concentrated, which is very large, but in very small space, is a curvature which is more and more deep. There are objects in the sky, consequence of the end of stars, which are a mass very concentrated due to the collapse of the stars at the end of its life. And if the sun is a curvature sufficient to show the ellipses in the motion of the planets, a white dwarf is something much pronounced, the neutron star is much enhanced, and the black hole is the maximum possible curvature. The gravity at the surface is so strong that not even the light, not even photons can leave this. And this is a very peculiar object in Einstein general relativity. It's something which the mass is only at the center, and this bubble, this black bubble all around, is the horizon, the event horizon, simply protect this point at the center. It's a black, big, like a soap bubble, which is empty outside, empty inside, just all the mass was collapsed at the center. And this is the maximum curvature, infinite curvature at the center. This is the mysterious black hole. If you enter, no way of coming out, no more. So it's something which is no more in our universe, in a sense, but it produces the maximum space-time curvature. So objects like that, when they move in this flexible, in this elastic space-time, generates waves, since space-time is some sort of elastic medium. So these waves are made of space-time perturbation. And this is an example of a wave propagating from two compact stars orbiting one to each other. The effect of the gravitational wave passing through space can be seen. I asked to the technicians there to just activate this. Okay, perfect. So you see, this is the effect of a gravitational wave passing through space. It's not a simple effect like the one of the electromagnetic wave, let's say. It's something which has a tidal motion, a quadrupolar motion. This is typical of the fact that gravity has not two signs, not plus and minus, like in the electromagnetic case. There is only one sign, only attraction. So this is a consequence of that. Is that the motion is of this type, tidal motion, let's say, transversal effect with respect to the direction of propagation. The effect is very small, as you will see, so this is why it has taken 50 years of experimental efforts to arrive to the detection. But the detection was waited so long and was considered so important because the objectives of gravitational research are very ambitious. The first is, of course, that you need to confirm general relativity even in this prediction, in the prediction of the dynamic wave propagating in space. The other is this: thanks to that, you can have information from dark side of the universe, dark region, dark objects which does not emit light. However, they need moving and accelerating to emit this kind of waves. There is a comparison which one can make with the sound with respect to the light. So electromagnetic waves, photons, are light in various bands, from X-ray, gamma ray to radio wave. Gravitational waves is like the sound because it's like the propagation of a perturbation in space, which is a deformation of space. Not a deformation of the atmosphere, of course, but even empty space change its shape. And this means that to look for objects like neutron stars, like black holes, understanding gamma ray bursts and various phenomena in the universe. Then there is a third objective, which is even more ambitious, is that gravitons decoupled from the original plasma much before photons. The cosmic microwave background is a picture of the universe when the universe was already 380,000 years old, which is very young, but, however, is not a pristine condition of the universe. Neutrinos decoupled almost 1 second after the Big Bang. Gravitons decoupled 10 to the minus 43 seconds after the Big Bang. So this is the probe which is more near to the origin of our universe. And so detecting a cosmic background of gravitational waves is a fundamental thing. But depending on the shape of the wave that we have, we can infer the sources. Like suppose this big room is completely black. You enter in this black room, you don't know what there is inside. But if you hear the sound of a violin or the sound of a piano, just one note, you know immediately, analyzing with your ears the wave, that there is an instrument there. If there is a piano, if there is a violin, what this is, even which note. If you are a musicist, even if the instrument is a very good instrument or is a bad instrument. So in the simple waveform, I have not to teach this to you, but in a simple waveform, you analyze mostly the electromagnetic waveform, but this is another kind of messenger. But however, there is a lot of information. And in fact, in a supernova, which is a short burst, there is information about the inner detailed dynamic of the supernova. One can see if what is formed is a neutron star of black holes and have nuclear physics, high density information. There are objects like pulsars, so spinning neutron stars. In this case, you can see which is the location, how many neutron stars are, and from the pulsation of the star, even some nuclear physics, which is impossible to do on the Earth. Coalescing binaries, the third is the most important because the wave we detected so far are of this kind, are the coalescence of two compact objects, black holes up to now, in which that spiraling together form from a binary orbit. They emit gravitational waves, so they lose energy, but the conservation of angular momentum make that they are going faster and faster up to the point of the merger. And this waveform reflects this dynamic behavior. So in this waveform, the information is the masses of the two objects. And in the amplitude when they merge, there is another fundamental information, the distance. Once you know the masses, looking to the amplitude, you know the distance of the source, independently from any other consideration. And this is true for our black object. You don't see, you just hear this wave. So this was the first man trying to detect gravitational waves. Actually, he put some big oscillators or big diapason, let's say, and the idea was that arriving on these instruments, you can put in vibration these objects, and so you can detect some coincidence between various of these big cylinders, big diapason. This is Joe Weber, his name. You see that he is trying to glue piezoelectric ceramic on the surface of this big cylinder. Piezoelectric ceramics are such that if there is a strain, they respond with an electrical voltage, and so they are very good transducers. Then all this technology didn't achieve the results. I mean, didn't arrive to detect gravitational waves. Sensitivity was not enough. And however, this technique learned to many people, including myself, how difficult it is to detect gravitational wave. You have to go to the limit of the technology in every aspect. Principally, you have to suspend the object perfectly with respect to the acoustic motion, seismic motion around, all electrical disturbances at the heart of any gravitation experiment since the time of Cavendish, and that was there is a mass which must be isolated from the rest of the environment. So we cooled down these objects to reduce the thermal noise. We use a superconducting electronic to reduce the electronic noise, but we didn't succeed. So we developed new instruments, and it was explored at CERN in earlier time. So these 50 years of attempts of detection, starting with Weber, arrived at the end to large interferometers. These objects, these large interferometers, like LIGO and Virgo, they succeeded to detect gravitational waves. And I would like that could be activated this animation in which you see this cylinder is the laser, this is a beam splitter, so the laser light, I know there are experts of lasers here, the laser lights in YAG goes to this beam splitter. It divides in two. One is this arm and one goes in this other arm. Come back after the reflection. They recombine and go to the photodetector. What happens? This is an instrument which is very sensitive to displacement. In fact, you see the beam splitter makes its work. It is to divide in two. This 3 or 4 kilometers long arm, the travel, so they arrive and they recombine. If they recombine in the opposite phase, there is black dot here, no spot. But if a gravitational wave arrives, then the quadrupolar nature makes that this goes shorter, this goes longer, and you see that the interference change here. And so you see that the intensity of light is a measure of the amplitude of the wave. The frequency of this changement is the frequency of the gravitational waves. So with this system, we succeeded in measuring gravitational waves. Actually, if you make a plot of frequency and of gravitational wave sensitivity, so the minimum strain you are able to detect, there are sources of noise, fundamental sources of noise, which are limiting the sensitivity, of course. At low frequency, you have seismic noise. In the intermediate part, you have the thermal noise of the suspension. And in the upper part, you have the shot noise to the photon counting. I mean, actually, there are 3 big interferometers of, let's say, advanced class, how we say. 2 are in the US and 1 is in Italy. The 2 in the US are very famous, is LIGO, and the one in near Pisa in Italy is Virgo. LIGO was funded some 1 or 2 years before Virgo, so LIGO entered in data taking before Virgo and made the first discoveries. However, Virgo and LIGO are considering themselves the same big collaboration. They share all the upgrades, all the new improvements, hardware and software, and they analyze together the data, they publish together the results. So at the end, going to the limit of sensitivity in seismic isolation, in the masses, in the coating of the mirror, in the high power stable lasers. I have no time to spend much. Believe me, there are no things that you can buy on a catalog. You have to develop, and years are needed to develop these things in such a way that the sensitivity goes low enough to allow the detection. And finally, on September 14, 2015, you see this is the noise of one interferometer LIGO in Hanford, Washington. This is, in blue, is the one in Livingston, Louisiana. This is the intrinsic noise, but you see the intrinsic noise at the moment took the shape of a wave, the same wave that the other have seen. Actually, if you subtract the noise, you can see that the same waveform arrived on the detectors. And in fact, this waveform tells us that there are 2 masses, one of 36 solar masses and another with 29 solar masses, which have formed a final mass of 62 solar masses. There are 3 solar masses converted in gravitational waves, 3 solar masses converted in energy, 3 solar masses converted in energy, which were out from this system. How we know there are black holes? Well, we know the masses, and this frequency tells us that they have rotated in one respect to the other at 150 Hertz. So this is only possible if the masses are so concentrated to allow them to arrive at this frequency without touching. So they must be black holes. And the speed when they finally merged was more than half the speed of light. So 2 masses, several solar masses, colliding at a speed which is more than half the speed of light. And this is what happened in another movie. This is the 2 black holes. You see this green part is the crest, the peak of the wave. So this happened more than 1 billion years ago. So for more than 1 billion years, the wave propagated through the universe, arriving at the Earth on September 14, 2015. Also, the Earth reacted to the gravitational waves. Now, this effect is very exaggerated, just to show you that everything, of course, reacted to gravitational waves. But this time, on the Earth, there were 2 fantastic instruments which they were able to finally detect a displacement of 1/1000th of a billionth of a meter, 10 to the minus 18 meters. It explains, I think, better than any other consideration why 50 years were needed. So this achievement was recognized not only because the website of Physical Letters crashed when this paper appeared, it was the first time in history, but also recently, a few days ago, let's say a few weeks ago, by the Nobel Prize in Physics, which was given by Ray Weiss of Massachusetts Institute of Technology, which was the person which first analyzed all the sources of noise over interferometers and made it possible to pass from a Michelson interferometer, which was known, of course, known since the measurement of the speed of light, arriving to a real instrument for detecting such an elusive wave. This is Barry Barish, which organized the LIGO scientific collaboration in such a way to arrive to these results effectively, and Kip Thorne, which was one of the founders of the LIGO, and also, as you know, he's made many calculations about black holes. So this was a recognition which the three said immediately had to be divided. I don't know if even the money will be divided, I don't think so, but the recognition at least will be divided with all the rest of the LIGO-Virgo collaboration. So why this results is very important, because after this first two black hole system, LIGO detected others mergers of two black holes. And this revealed to us black holes of unknown mass. You remember Galileo saw for the first time these three things which were unpredicted, but we saw things which were unpredicted. In fact, all the known black hole in the universe that we, as astronomers late, not we, have detected, were detected up to now, before this LIGO observation, with the accretion disk from a normal star, big normal star, to something very small and very massive, which was supposed to be a black hole. But what was measured was X-rays in a small region. And so we inferred the existence of black holes already of this kind of masses. But all the masses which have seen the LIGO system are very big objects which were unpredicted. So this means that there are more black holes in the universe than we thought. And how many more? Well, there are papers which are trying to calculate that. This is too early to say something definitive, but however, the idea is that in principle, could be so many. This is the question. There could be so many that to explain the dark matter in the universe. This will be fantastic to have discovered at the same time black holes, gravitational waves, and dark matter. But this is too early to say something about that. What is not too early to say, is that also Virgo entered in data taking, and measured a new couple of black holes merging. Why this was important? It was important because with 3 detectors you can recognize, you can resolve the region of the sky where the source was. With 2 detectors, only with two LIGO, you define some very well, I will show you this, which is just how we detected the last merging of black holes. The localization with only the 2 LIGO is this one, you see? If you add Virgo, then the localization is more precise. And then, if you have a wave from that point, you can say to all the optical telescope, gamma telescope, X-ray telescope, to point, this is very important, to point that part of the universe and look what happens exactly there. This is the multi-messenger astronomy, a new chapter, let's say, of astronomy, which is to follow a gravitational wave source in all the electromagnetic band. This is just at the beginning. Up to now, only black holes have been detected, so no photons, only upper limits. Let me say that you have to stay tuned, because on on Monday, October 16, 10 a.m. in Washington, 4 p.m. here in this part of Europe, there will be a release of new results coming from LIGO Virgo and many other electromagnetic observatories. So if you have something to do at 4 p.m. on Monday, leave any other things and just tune it is worth. Of course, all the gravitational wave field took a boost from these results, and so we are thinking to new detectors. One is an underground detector to reduce seismic and Newtonian noise, 10 kilometers arm long, Einstein telescope, we call it. This is only a project for now, but this will, of course, see much more, many more sources and more far in the universe. Another project, a fantastic, fascinating project, is to send an interferometers in the sky in heliocentric orbit with arms that will be not a few kilometers, but a few million of kilometers. And that will be fantastic to measure very low frequency waves, like the waves emitted by massive black holes, the supermassive black holes, which are at the center of almost every galaxy, for instance. So the field just started, the gravitational wave field. The gravitational astronomy has just started its I think, long history, which will revolutionize, I think, the astronomy. So we started with the notebook of Galileo, with the beginning of modern astronomy with the electromagnetic wave. We arrive to this vibration of the universe. So we had the sight, we had the eyes. Now we have also the hearing about the universe. This is the big new. And I think that the universe will appear to us now more rich, and there is a new way of experiencing the universe, and this is too early now to say how many more things we will learn. For sure, as Marcel Proust said, the real travel is not to do, the travel of discovery is not to see landscapes, but to have new eyes. Nothing will be as before. Thank you very much for your attention.
Thank you, Professor Coccia. So I'm sure you have some questions. So we have some time to receive questions.
Congratulations, it's very clear, and thank you.
Thank you.
I have a question concerning the detector, because as far as the Earth is concerned, I know that there is a lot of movement linked to tectonic pressures, and this movement may be much higher than the gravitational waves effect. How do you differentiate between natural wave of the ground and the gravitational waves?
Well, first of all, we have seismometers everywhere on the ground, so we correlate, of course, and then we know that the level of isolation of these masses in all the range of frequency of seismic noise is a source of noise. In fact, it's limiting the noise at low frequency, but this limitation means that in all the region above a few hertz up to several kilohertz, the sensitivity is the nominal one, which I said. And also, I think that the many instruments that we have takes under control this the source of noise. Of course, the Newtonian noise is much more subtle enemy, because the Newtonian noise is not directly the seismic one, but is the one coupled to the Newton force. Is the revenge of Newton, because the surface wave on the Earth makes the mirror attracted to one part of the floor respect to the other, depending on the distance of the floor. This is the Newtonian noise, which you cannot shield it. You have to reduce it. And reducing, the only way effective to reduce it is to go underground, where the surface wave is much reduced. This is why we think to an underground detector.
Okay. Yes, next one.
Oh, thank you very much for the presentation. Well, last year in PCAPEC in Brazil, we had the privilege to receive there Jameson Rollins from LIGO, and he talked about this probability to use an outer space interferometer to make measures. So you mentioned that before LIGO, we had unpredictable number of gravitational waves occurring in the universe. Do you think if it was possible to implement something like that in outer space, we could not only measure many more gravitational waves in the universe, but also found something is hide to the scientific community today?
Well, I'm not sure if I understood the question.
If you think that improving the technology, but not only the technology, removing all the seismic noises of the Earth, implementing something in outer space or interferometer in outer space.
Yes, of course.
It's possible to reach something that is not nowadays knowledge.
So the ultimate way to get rid of seismic and internal noise is to go to space. In fact, the LISA project, it can go to low frequency, to frequencies in which you cannot have a detector on the Earth, where there is a sort of wall at 1 Hertz. So going to space open to you all the low frequency part of the spectrum. This low frequency part of the spectrum can allow you to detect different sources respect to the one with kilohertz, with audio frequency range, because these interferometers are audio frequency range, let's say, and can detect objects which are very fast, let's say. LISA open the low frequency part of the spectrum, so can look, for instance, can observe binary stars far from the coalescing phase. Actually, what would be wonderful is that LISA can set an alarm to the other Earth-based detector saying, look, in 1-2 days there will be a merging, because we are seeing the part of the wave at low frequency that then will arrive chirping at high frequency. And in fact, there are binary stars which will provide the calibration of LISA. So this is the first detector which actually starts with dominated by signals and not by noise. The big, let's say, the goal, the main goal maybe, is to detect supermassive black holes. These supermassive black holes are millions or billions of solar masses that are merging also of that kind of monstrous object in the universe. And also LISA can detect, can try to detect the stochastic background in that part of the region of the frequency in which theory says that that could be something. So this is, it is a new science that will open.
Okay, we have, okay.
What is the accuracy with which your gravitational wave detectors can pinpoint the location on the sky, and what sort of accuracy will you be able to achieve with future observatories?
So how the improvement in sensitivity, you mean?
No, in terms of the location of the potential object that another observatory could look at.
Well, thank you for this question. I think that, you see, when you open a new astronomical window, always you had surprises. When you open the optical window with Galileo, no one had predicted the Jupiter moons. When you open the X-ray or even the gamma ray window, gamma ray burst was a surprise. No one predicted them. Also, the cosmic microwave background was something which was believed to be a background noise of the instrument and not a cosmic object at the beginning. So also opening this window, we had a surprise. In fact, we expected neutron stars to be neutron stars merging to be most numerous of black holes merging. And this was wrong, because these black holes, which have dominated the observation up to now, have been much more in number than we expected, the rate of event. So what we want to open is the chapter, let's say, on binary neutron stars, and in fact increasing the sensitivity of a factor of 10, which we want to do with the Einstein telescope. Then this opened the way to not only to neutron star merging, but also to neutron stars pulsar, the monochromatic wave which coming from them. So the rate of event will pass from the overall from 1 per 2-3 months, like now, to several per days. So this means really, because you see, when you change a factor 10 in amplitude, you change a factor 10 in distance. H, the amplitude of the gravitational wave, goes like the distance. So a factor 10 in distance means a factor 1,000 in volume. So a factor 1,000 in rate of event. So this is why we are very optimistic of many, many surprises and sources, predicted sources and unknown, maybe.
Okay, unfortunately, time is limited, so we have to close the session. So let's thank to Professor Coccia.
Thank you.